Welcome to Lecture 6 of Geometric Physics 1. Today is called Linear Symplectic Geometry. The reading is Marsden and Ratiu, Chapter 2, together with Frankel, Section 4.4. For next time, read Marsden and Ratiu, Chapter 5, on symplectic manifolds and Darboux's theorem. 5 lectures of geometry are now behind us. The review is over. From here on, this course is mechanics, and today Marsden and Ratiu opens. 5 lectures of geometry are behind us. Today, the object that the rest of this course is about finally walks in. The interior product of xh with omega equals dh. Everything today happens on a vector space. Lecture 7 moves the same structure onto a manifold. There are 4 stops. First, symplectic forms on a vector space. They are antisymmetric and nondegenerate, and that pair of adjectives forces the dimension to be even. Second, symplectic maps, the symplectic group, and the reason they preserve volume. Third, Hamilton's equations written without coordinates, plus a test for deciding which systems of differential equations are Hamiltonian. Fourth, Poisson brackets, conserved quantities, and a bead sliding on a rotating hoop. Now the idea to carry through the hour. An inner product is symmetric, and it gives you length and angle. A symplectic form is antisymmetric, and it gives you neither. What it gives you instead is dynamics. It is a canonical recipe for turning a function into a vector field. We begin with linear algebra, 1 bilinear form, 2 adjectives, and the whole geometry of phase space follows from them. Let Z be a real vector space. A bilinear map omega is antisymmetric if omega of Z and W equals minus omega of W and Z. It is non-degenerate if the only vector Z whose pairing with every W vanishes is Z equal to 0. A symplectic vector space is a Z carrying such an omega. Non-degeneracy has a cleaner phrasing. Define omega flat to be the map sending Z to the interior product of Z with omega. Non-degeneracy then says that omega flat is injective, an infinite dimension that makes it an isomorphism onto the dual space. The standard example is one we have been circling for 3 lectures. Take Z to be Rn cross Rn. Define omega of 2 vectors to be q dotted with p prime minus q prime dotted with p. That is the same as the sum over I of dq I wedge dpi. It is the omega equals minus d theta of lecture 3, frozen at one point of t star q. Now the thing to keep. Omega flat is an isomorphism from Z to its dual build with no metric at all, and it is what converts dh, a covector, into a velocity. Fix a basis of Z, and let M be its dimension. Then omega of Z and W becomes Z transpose, AW for some matrix A. Antisymmetry says A transpose equals minus A. Non-degeneracy says the determinant of A is not 0. The proposition is this: a non-degenerate antisymmetric bilinear form exists only in even dimension. The proof is one line. The determinant of A equals the determinant of A transpose, which equals the determinant of minus A, which is minus 1 to the power m times the determinant of A. If m is odd, that says the determinant equals minus itself. So the determinant vanishes and omega is degenerate. 2 consequences deserve separate billing. An inner product suffers no such obstruction. Symmetric positive definite forms exist in every dimension. Even dimensionality is forced by antisymmetry alone. Second, set W equal to Z, then omega of Z with itself equals minus itself, so it vanishes for every single Z. Every vector is omega orthogonal to itself. That second one is the one to keep. Nothing in the theory is a candidate for the length of Z, because the only quadratic expression omega offers vanishes identically. Phase space is even dimensional, and phase space has no ruler. Now the normal form. Let Z with omega be symplectic of dimension 2n. Then there is a basis E1 through En and F1 through Fn with 3 properties. The E's pair to 0 among themselves, so do the F's. And omega of EI with Fj is the Kronecker delta. Such a basis is called a symplectic basis. In it, the matrix of omega is the standard block matrix J, with the identity above the diagonal and minus the identity below. So omega of Z and W is Z transpose JW, and omega is again the sum of dq wedge dp. The proof is symplectic Gram-Schmidt. Pick any non-zero E1. Non-degeneracy hands you an F1 with omega of E1 and F1 equal to 1. The plane they span is symplectic, so Z splits into that plane and its omega orthogonal complement, which is symplectic again. Then induct. So all symplectic vector spaces of a given dimension are isomorphic. There are no local invariants and no analog of curvature. On manifolds this survives, and it is Darboux's theorem. Every symplectic manifold looks flat near every point. Metrics do not, and Lecture 7 proves it. Put the two structures side by side. An inner product is symmetric. A symplectic form is antisymmetric. Feed an inner product one vector twice, and you get a positive number, the square of a length. Feed omega one vector twice, and you get 0, which is no information at all. An inner product lives in any dimension. A symplectic form needs an even one. Both have a normal form, orthonormal in one case, symplectic in the other. Their symmetry groups are the orthogonal group and the symplectic group. One extra row is worth naming. A subspace equal to its own omega orthogonal complement is called Lagrangian. Those have dimension n, and there is no metric analog, because a subspace and its perpendicular always meet only at 0. Generating functions and Hamilton-Jacobi theory all live there. Now the last row, and the reason for the whole comparison. The gradient of f points across the level sets of f. The Hamiltonian vector field xf points along them, because df applied to xf is omega of xf with itself, which is 0. That single sign flip is the difference between relaxation and conservation. It separates a gradient flow that runs downhill from a Hamiltonian flow that conserves energy. Next, the maps that preserve a symplectic form. They are the canonical transformations, and they turn out to preserve volume for free. A linear map T is symplectic, or a linear canonical transformation, if the pullback of omega by T is omega again. Spelled out, omega of Tz and Tw equals omega of Z and W. In a symplectic basis that reads T transpose, J, T equals J. Since J is invertible, so is T. Inverses and composites of symplectic maps are symplectic, so they form the symplectic group, written SP of 2n and R. Take n equal to 1. The matrix condition then collapses to the single equation determinant of T equals 1, so the symplectic group of the plane is exactly the special linear group. In one degree of freedom, canonical means area preserving and nothing more. Its Lie algebra consists of the matrices A satisfying A transpose J plus JA equal to 0, and it has dimension n times the quantity 2n plus 1. Keep that set in view. It reappears in 10 minutes wearing a different hat. The idea to keep is this. Canonical transformations are not a computational trick for solving problems. They are the automorphisms of the structure, exactly as orthogonal maps are the automorphisms of an inner product. Everything a symplectic form can express is invariant under them. Take determinants in the relation T transpose Jt equals J. That gives the determinant of T squared equal to 1, so the determinant is plus or minus 1. To rule out minus 1, we need the top form. Define capital lambda to be 1 over n factorial times omega wedged with itself n times. In canonical coordinates, that is dq1 wedge dp1 and so on through dqn wedge dpn. It is a non-zero form of top degree, and saying it is non-zero is non-degeneracy restated. Now suppose T preserves omega. Then T preserves every wedge power of omega, so T preserves capital lambda. But for a linear map, pulling back a top form multiplies it by the determinant. Hence the determinant of T is 1. Symplectic maps therefore preserve volume and orientation. The converse fails badly once n exceeds 1. The symplectic group in 4 dimensions has dimension 10, while the special linear group there has dimension 15. So volume preservation is a consequence of being symplectic, not a restatement of it. The extra rigidity is real. Gromov's non-squeezing theorem says a ball cannot be symplectically squeezed into a thin cylinder, however much room the volume allows. Now mechanics. One equation defines the Hamiltonian vector field, and everything else this hour is a consequence of it. Let z with omega be symplectic, and let h be a smooth, real-valued function on z. The Hamiltonian vector field xh is defined by a single equation. The interior product of xh with omega equals dh. Hamilton's equations are then z dot equals xh of z. xh exists and is unique precisely because omega flat is an isomorphism. We just apply the inverse of omega flat to dh. Non-degeneracy is what makes mechanics possible. Now go to coordinates. Write xh with components a along the q directions and b along the p directions, and test it against an arbitrary vector with components c and d. The left side gives a dotted with d minus c dotted with b. The right side gives the partial of h with respect to q against c, plus the partial of h with respect to p against d. Matching them gives an equal to the partial of h with respect to p, and b equal to minus the partial with respect to q. Those are Hamilton's equations. Compactly, z dot equals j times the gradient of h. And the minus sign is not a convention that anybody chose. The minus sign is the antisymmetry of omega transcribed. Suppose someone hands you a vector field x on z. Is there an h with x equal to xh? We need the interior product of x with omega to be d of something. Here is the theorem. X is Hamiltonian if and only if the one form obtained as the interior product of x with omega is closed. Equivalently, the derivative of x at every point must be omega skew. That is, omega of dx u and v equals minus omega of u and dx v. On a vector space, closed implies exact. So the test is decisive, and h is determined up to an additive constant. Take the linear case. For x of z equal to az, the condition becomes a transpose j plus ja equal to 0. Equivalently, a is j times s with s symmetric, and then h of z is 1/2 of z transpose s z. Look at that condition again. It is word for word the definition of little sp of 2n and r from earlier. The linear Hamiltonian systems are the Lie algebra of the symplectic group. Being Hamiltonian is the infinitesimal form of preserving omega, and that is why the next result is inevitable. Take the plane with omega equal to dq wedge dp and a general linear system with matrix A. Compute the skewness condition, and everything cancels except the trace. So the system is Hamiltonian if and only if the trace of A vanishes, and then H is the obvious quadratic form. Two quick cases. The oscillator has trace 0, and the recipe returns the familiar energy. Damping fails. Add a term minus gamma p to p dot, and the trace is minus gamma. That flow shrinks every area exponentially, and no symplectic flow can do that. Nonlinearly in the plane, take x with components f and g. The interior product of x with omega is f dp minus g dq, and its exterior derivative is the divergence of x times dq wedge dp. So, on the plane, Hamiltonian means exactly divergence-free, and h is the stream function. But once n is at least 2, divergence-free is necessary and no longer sufficient. So a planar Hamiltonian system is an incompressible plane flow, and its Hamiltonian is the stream function. Level sets of h are the trajectories, which is why energy contours work in 1 degree of freedom. Now, the central theorem, let phi sub t be the flow of xh. Then the pullback of omega by phi sub t is omega for every t. Equivalently, the derivative of phi sub t is symplectic at every point and time. The proof is 2 lines. By the dynamic Lie derivative formula from lecture 5, the time derivative of the pullback of omega equals the pullback of the Lie derivative of omega along xh. Cartan's magic formula evaluates that Lie derivative. It is d of the interior product of xh with omega plus the interior product of xh with d omega. The first term is d of dh, and the second contains d omega, so both vanish. The pullback is therefore constant, and at time 0 it is omega. Both terms earn their keep. The first dies because d of d is 0. The second dies because omega has constant coefficients. On a manifold, we will simply demand that d omega vanish, and this proof is why. 2 lines and no computation. The content is d of d is 0, together with Cartan's formula. and it says something enormous. The time evolution of any mechanical system is a canonical transformation. The corollary is Liouville's theorem. The flow of xh preserves the phase volume capital lambda. The reason is that pulling back a wedge power is the wedge power of the pullback, and we just showed omega comes back unchanged. In coordinates, the same statement is that the divergence of xh vanishes, and even that is mixed partials again. The q derivative of the partial of h with respect to p and the p derivative of minus the partial of h with respect to q cancel each other. It is worth being concrete about what this rules out. A region of initial conditions may stretch and fold beyond recognition, but its volume never changes. So a Hamiltonian system has no attractors, no asymptotically stable equilibria, no limit cycles, no strange attractors, no friction of any kind. Add a bounded energy surface and you get Poincaré recurrence. Almost every initial condition returns arbitrarily close to where it started. So Liouville's theorem is not a separate physical principle. It is one wedge power of the statement that the flow preserves omega, which was itself one line of Cartan's formula. The invariant measure that all of statistical mechanics rests on comes from exactly that. Last section. The Poisson bracket packages everything so far into one operation. Then a bead on a spinning hoop puts it all to work. For functions f and g on z, define the Poisson bracket to be omega of xf and xg. Since the interior product of xf with omega is df, it also equals df applied to xg. In canonical coordinates, it is the familiar sum. Take the partial of f with respect to qi times the partial of g with respect to pi. Then subtract the same product with f and g interchanged. The coordinates bracket to 0 among themselves, and the bracket of qi with pj is the Kronecker delta. The bracket is bilinear and antisymmetric, obeys Leibniz's rule, and obeys the Jacobi identity. So the smooth functions on z form a Lie algebra, and the map sending f to xf turns a bracket into minus a commutator. Jacobi is no accident. It is the statement that d omega vanishes in disguise, which is why closeness becomes an axiom next lecture. The Poisson bracket is the classical shadow of the commutator. Dirac's rule replaces the bracket by the commutator of the corresponding operators divided by IH bar. That turns the bracket of Q with P into the canonical commutation relation. Quantization looks for a map respecting this structure. Let z of t solve Hamilton's equations, and let f be any function on z. Differentiate f along the solution. You get df applied to xh, which is omega of xf, and xh, which is the bracket of f with h. So f dot equals the bracket of f with h. That single equation replaces the whole system. Take f to be a coordinate or a momentum, and Hamilton's equations come back. Now the consequences. A function f is conserved exactly when its bracket with h vanishes. The bracket of h with itself is 0 by antisymmetry, so h is always conserved. Energy conservation is antisymmetry. If f and g are both conserved, so is their bracket. That is Poisson's theorem. Notice the relation is symmetric in the two functions. Read one way, f is constant along the flow of h. Read the other way, h is constant along the flow of f, so f generates symmetries. Those two readings are the same equation. A conserved quantity and a symmetry are one object seen from two sides, and a vanishing bracket is the whole of Noether's theorem in this setting. The non-abelian version, the momentum map, arrives in lectures 13 and 14. Here is the example that runs through the chapter. A bead of mass m slides without friction on a hoop of radius r. The hoop is driven about its vertical diameter at constant rate capital omega. Let theta measure position along the hoop from the bottom. The speed has two orthogonal pieces. One is r times theta dot along the hoop. The other is capital omega times r sine theta around the axis. The height is minus r cosine theta, so the Lagrangian is 1/2 mr squared times theta dot squared plus capital omega squared sine squared theta, all plus mgr cosine theta. The conjugate momentum is mr squared theta dot, and the Legendre transform gives the Hamiltonian. It is the momentum squared over 2mr squared plus an effective potential, namely minus mgr cosine theta minus 1/2 mr squared, capital omega squared, sine squared theta. Now the subtlety. H is conserved because the bracket of H with itself is 0. But H is not the total energy. The constraint is time dependent. So whatever drives the hoop does work on the bead. Energy and the conserved quantity have parted company, and only the conserved quantity generates the dynamics. Differentiate the effective potential, you get mr sine theta times the quantity g minus r, capital omega squared, cosine theta. So the equilibria come in two families. The bottom and the top of the hoop are equilibria at every rotation rate. In addition, there is a pair at plus and minus theta naught, where the cosine of theta naught equals g divided by r capital omega squared. That pair exists only when the rotation rate reaches a critical value, and the critical value is the square root of g over r. Stability comes from the second derivative of the effective potential. At the bottom it equals mr times the quantity g minus r capital omega squared. That is positive exactly when the rotation rate is below critical. At the new pair of equilibria, it equals mr squared capital omega squared sine squared theta naught, which is positive whenever those equilibria exist at all. So spin the hoop slowly and the bead rests at the bottom. Spin it past the critical rate and the bottom becomes unstable, while two new stable positions appear on either side. This is a supercritical pitchfork bifurcation, and the bead must choose a side. It is a mechanical system breaking its own symmetry. Compare the two phase portraits, with theta running across and the momentum running up. Below the critical rate, there is a single center at the bottom of the hoop, ringed by closed orbits, and a saddle at the top. Above the critical rate, the bottom has turned into a saddle, and two new centers sit on either side of it, each ringed by its own family of closed orbits. Orbits are level sets of H, so nothing spirals inward or outward. Liouville forbids it. Past the critical rate, the bottom equilibrium becomes a saddle and grows a homoclinic figure 8, whose two loops enclose the two new centers. That figure 8 is fragile. Modulate the rotation rate slightly in time and the loop breaks. The stable and unstable manifolds of the saddle no longer join smoothly. They miss each other and cross transversally instead. The Poincaré-Melnikov function measures the gap between them, and a simple zero of that function forces a Smale horseshoe, and therefore chaos. Marsden and Ratiu, section 2.9, does this properly. We will not. 8 things from today. 1. A symplectic vector space carries a non-degenerate antisymmetric omega. Antisymmetry alone forces even dimension and kills any notion of length or angle. 2. Every such space has a symplectic basis, in which omega is the standard sum of dq wedge dp. No local invariance, no curvature. Darboux next lecture. 3. Preserving omega defines the symplectic group, and every symplectic map has determinant 1. 4. Hamilton's equations say the interior product of xh with omega equals dh. In coordinates, that is, q dot from the p derivative of h and p dot from minus the q derivative. 5. A vector field is Hamiltonian exactly when its interior product with omega is closed, which in the plane means divergence-free. 6. Flows preserve omega by Cartan's formula, hence preserve volume. Liouville, and no attractors. 7. The bracket of f and g is omega of x, f, and xg, and f dot is the bracket of f with h. Conserved quantities Poisson commute with h, and each generates a symmetry. 8. The rotating hoop gave a conserved h, that is not the energy, and a pitchfork at the critical rate. Next time, Marsden and Ratiu, Chapter 5. Today's linear algebra moves onto a manifold. Closeness becomes an axiom, and Darboux ends the local story. Lecture 8 returns to T star Q.